I want you to do something right now. Open Google Earth. Find any open pit mine. The Bingham Canyon copper mine in Utah. The Chuquicamata Quarry in Chile. The Mere diamond mine in Yakutia. Look at the shape. The terraces. The spoil heaps around the edges. The way the earth descends in concentric rings. Remember that image. Now find the Himalayas, or the Andes, or the Rocky Mountains. Now tell me, what's the difference? Because I've been looking at these images for several years now, and the difference becomes less obvious every time. Official science tells us that mountains are the result of tectonic processes, colliding plates, millions of years, rock slowly being pushed upward. Fine, but then explain something to me. Why do mountain ranges look like spoil heaps? Why do the valleys between them have the shape of quarry excavations? Why are the richest mineral deposits on Earth located precisely where, according to the official version, rock was pushed upward? And the most important question of all, who said any of this happened without the involvement of intelligence? Let's start with the basics. When a mining company works a deposit, it extracts the useful material and has to put the waste rock somewhere, the part that isn't needed. It gets stacked to the side of the excavation. The result is a characteristic shape, a spoil heap. A spoil heap has several defining features. First, an irregular but organized shape. Not random chaos, but not natural symmetry either. Second, a terraced structure. Rock is stacked in layers, in steps. Third, positioned around or alongside a central excavation. Fourth, composition. A spoil heap consists of less valuable rock, what remains after the useful material has been extracted. Now take any mountain range of the middle latitudes, the Urals, the Appalachians, the Atlas Mountains in Africa. Check each of those four features. Irregular but organized shape, yes. Terraced structure, yes. Geologists call it stratification, but visually these are the same stepped formations, positioned around a central excavation, yes. And that excavation is called a valley or a basin. Composed of less valuable rock? Yes. The richest veins are found inside, not on the outer surface. I'm not saying this is proof. I'm saying this is a coincidence that deserves a question. Here is a fact that appears in any geology textbook, but that nobody emphasizes. The Earth's crust is uneven. Where the mountains are, the crust is thinner, not thicker. Thinner. Wait, if mountains are rock that has been pushed upward, then there should be more material beneath them. The crust should be thicker. That's intuitively obvious. But geophysical data shows the opposite. Beneath many mountain systems, the crust is anomalously thin, especially in zones of active mountain formation. The official explanation, isostasy. Rock essentially floats on the mantle, and the greater the mass of the mountain above, the deeper it sinks below. So the crust beneath mountains extends downward in roots. This explanation is mathematically sound, but it describes the same picture you would see if you looked at a quarry in cross-section. Where material has been extracted, the surface drops. The walls of the excavation rise upward. The crust around the excavation becomes thinner as you move away from the edge. Isostasy and quarry excavation produce the same geophysical signature. This is not a refutation of official geology. It is an observation that two different processes can look identical from the outside. Now let's talk about resources. Here is the distribution of the world's largest mineral deposits. Copper, the Andes, Chile, Peru. A mountain belt. Gold, the South African highlands, the Urals, the Appalachians. Mountain and foothill zones. Iron, the iron ore belt of Brazil. A mountain plateau. Coal, the foothills of every major mountain system. The Appalachians, the Urals, the foothills of the Himalayas. Oil, sedimentary basins that geologists call intermontane depressions. Do you see the pattern? The richest resource zones on Earth are either the mountains themselves or the territories immediately surrounding them. Official geology explains this through tectonic processes. Mountain formation lifts rock, concentrates minerals, creates conditions for the formation of veins. But there is another way to read this map. If someone had been extracting resources from the earth on an industrial scale, what would remain on the surface? Waste rock, spoil heaps, slag mounds, ridges. And where would the excavations themselves be? Where the valleys are now, the basins, the intermontane depressions, the sedimentary bowls. The map of resource distribution and the map of mountain terrain are the same map. Just read from opposite sides. Let's talk about specific shapes. Take the Urals, one of the oldest mountain ranges on Earth by official classification. Age, approximately 300 million years. The Urals are a linear range. They run almost perfectly north to south for 2,500 kilometers. Deviation from the meridian is minimal. Natural tectonic processes do not create such perfectly linear structures. The collision of plates is a chaotic process. It creates arcs, curves, and nodes, not straight lines. But if you are cutting a trench or a channel for extraction, you cut it straight, because that is more efficient. Now look at the Appalachians, parallel ridges, remarkably regular, almost identical in height, separated by valleys of almost identical width. Geologists call this folding. Rock crumpled into folds like a rug being pushed from two sides. Visually, it resembles folding, but it also resembles a system of parallel excavations with spoil heaps between them. Morocco, the Atlas Mountains, linear ridges with regular transverse valleys, the world's richest phosphate deposits in the sedimentary basins at their base. Mongolia, the Altai Mountains, perfectly linear ridges oriented along the meridian, the largest deposits of rare earth metals. The pattern repeats on every continent. Now I want to say something about volcanoes. The official version, a volcano is a place where magma breaks through to the surface through cracks in the crust. Nobody disputes the physical mechanism. But let's look at the distribution. Volcanoes are located along tectonic fault lines. This is well known. The Pacific Ring of Fire, the Mid-Atlantic Ridge, the East African Rift Zone. But here is what's interesting. The mining industry uses a method called in situ leaching. The principle, a solvent is pumped into the ground, dissolving the target minerals, and the solution is then pumped back out. This requires a system of wells, injection wells, and extraction wells. If you imagine the Earth as a giant quarry in which something similar was applied, what would remain of that well system after millions of years? Channels in the crust through which molten material moves, periodically breaking through to the surface. I am not claiming that volcanoes are artificial shafts. I am claiming that their distribution suspiciously coincides with what a planetary-scale extraction system would look like. Here is a calculation I want to offer you. The volume of the Himalayan massif above the level of the surrounding plateau, approximately 4 million cubic kilometers of rock. Where did that rock come from? The official answer, from the collision of the Indian and Eurasian plates. Rock was compressed and pushed upward. Fine. But rock doesn't come from nowhere. If it was pushed upward, then somewhere there must be a corresponding void, a place from which that rock came. Geologists point to the Indian Ocean and the Tibetan Plateau as the sources. The Indian plate slides beneath the Eurasian plate. This is called subduction. But the Tibetan Plateau is itself one of the geological anomalies of the Earth. It is an enormous flat surface at an elevation of 4,500 meters. Area, 2.5 million square kilometers. Geologists call it the roof of the world. Here is a question that few people ask. Why is the roof of the world flat? Tectonic processes do not create flat surfaces on this scale. They create crumpled, fractured, uneven terrain. a flat surface of enormous area at great elevation, is what remains after large-scale removal of the upper layer. I am not a geologist, and I am not asking you to abandon official geology. Official geology correctly describes the physical mechanisms. Plate tectonics is real. Volcanism is real. Erosion is real. But a physical mechanism and a cause are two different things. Water flows downhill. That is the physical mechanism. But water flows downhill because someone dug a channel. That is the cause. The mechanism is identical, but the picture is completely different. What I am offering you is a way to look at the surface of the Earth not as the result of blind natural processes, but as the result of processes that may have had a purpose. Because when you look at mountains as spoil heaps, you start asking different questions. What were they mining? How much did they extract? For how long? Where did what they extracted go? And the most important question of all, who was doing the mining? Because the scale of what we see on the surface of the Earth is incomparable with anything humanity has been capable of producing across all of recorded history. But it is entirely comparable with what a civilization would leave behind if it had been working here long before us and left us its spoil heaps, which we call mountains. Subscribe. In the next video, we will look at exactly what may have been extracted and where it could have gone.